So thank you very much, everybody. To this PMIP Wings, so interactive, or I can't even remember what it stands for now, actually. But anyway, discussion series of seminars, and what I'm planning on doing is we're going to work through some of the themes that CMIP 7 has picked out as being important themes. And so those were thinking about the carbon cycle, thinking about extremes, and my brain's gone as to what the other one was, but then one of them is thinking about the pattern effect. And so I'm going to, and so perhaps I ought to do a brief introduction on the pattern effect but so this is really the idea that the warming we see in models is not the same as the warming that we're observing in the real world, and whether that has consequences, and whether it implies there's some issues with our models. And that sort of, I suppose, has really only become a topic in the past maybe 4 or 5 years, as the warming pattern in observations has really been fully established, and we're now confident that it's robust. And so we're going to be walking through those various different CMIP 7 science goals and seeing how paleo might help address some of them. And so it's my pleasure to invite 2 speakers today, and we're going to start off with Alicia, who is going to be talking about her research that she's been doing, thinking about the sort of mainly the tropical Pacific and patterns of warming in the tropical Pacific. And so I'll pass over to you now, and maybe you can give a bit of an introduction to yourself as well.
So it's my pleasure to talk to you about tropical Pacific upper ocean patterns during the last glacial maximum. So I'm currently based in Bordeaux in France, but I did this work during my postdoc while I was at National Taiwan University. And I was working with Ling, switch this to a laser pointer here, and we did this work with Lucas Yonkers and Heather Ford. So I'm probably going to be repeating, Chris, exactly what you just said. So I'll just quickly introduce the pattern effect, although I'm sure everyone's already very familiar. So what we're looking at here is the predicted pattern of surface warming in response to an increase in radiative forcing. And what's obvious is that the warming is not even everywhere on Earth. For example, you have more warming in the Arctic. And for my talk, I'm going to focus mostly on the tropical Pacific Ocean. And if we then zoom in on the tropical Pacific, we can compare what's the observed pattern from 1979 to 2014 versus the predicted pattern. So the observed is on the left-hand side and the predicted is on the right-hand side. And what we can see here is that the observed versus the predicted sea surface temperature pattern is very different. So the observed pattern, we see more warming on the western side and even some cooling in the eastern tropical Pacific, while in the predicted pattern, we see more warming on the eastern side and much less in the west. And these 2 different patterns are associated with a completely different set of radiative feedbacks. So with this pattern, you get a lower estimate of equilibrium climate sensitivity. And then with this type of pattern, you get a higher value. So it's obviously then very important in the future, under increasing greenhouse gas warming. Are we going to see something like this or something like that? Because they're associated with different radiative responses. And but comparing the observed response to the predicted response is not exactly a one-to-one comparison, because this is, I think, like a transient response to an increase in CO2, whereas the predicted response is a equilibrium response to CO2 forcing. So it's a little bit like comparing apples and oranges. But what we can do with paleoclimate data is we have proxy data and model simulations from past periods, which in theory both represent equilibrium responses. So we can then compare those to see if they show the same pattern or different patterns. So this is what we did in this work, which was published recently. So we looked at the last glacial maximum, which is obviously not a high CO2 interval that's a good analog for future warming. But it is characterized by very different greenhouse gas levels compared to present day. So we think that it still helps to provide some meaningful insight into how the tropical Pacific temperature pattern might respond to different greenhouse gas forcing. And we also chose to focus on the last glacial maximum because there's plenty of proxy data to facilitate regional comparisons rather than site-to-site comparisons, which has been done in the past. And there's obviously also available model outputs from PMIP. So the two main questions that we wanted to answer were, so during the LGM, under a cold equilibrium climate state with reduced greenhouse gas forcing, what was the upper ocean pattern in the tropical Pacific like? Did we see a reduced zonal SST gradient or a larger gradient? And of course, you also want to compare whether models and proxy data agree, or do they show the same pattern of warming or something different? So this is a map of the tropical Pacific Ocean showing our three different study regions. So we split the tropical Pacific into three different domains: the Western Pacific Warm Pool, the Eastern Pacific Warm Pool, and the Eastern Equatorial Cold Tongue. And within each of these three domains, we compiled proxy data. So we only compiled core sites that had both sea surface and subsurface temperature data. And it'll become apparent later on why we need both, but we do. And we then generated domain average values by averaging all the proxy data within a single region to get what we think is a more regionally representative value compared to just a single site, for example. And for the model side, we used all available PMIP 3 and 4 models that had seawater temperature outputs for both the LGM and the mid-Holocene. And it was only 7 models in the end, but better than one. And we used these black boxes to generate, again, regional values that we could compare with the proxies. So before I move on to the results, I should clarify some terminology. So following the convention of past studies from this region, we use the terms La Nina-like and El Nina-like to describe kind of the two main types of upper ocean patterns in this region. So when we refer to the pattern as being La Nina-like, so here we're looking at sea surface temperatures. So a La Nina-like pattern is characterized by a large gradient between the eastern and western tropical Pacific Ocean. And it's also characterized by a steep zonal thermocline tilt. So this is the 20 degrees Celsius isotherm in this figure, which we're using to approximate thermocline depth. And when we refer to the pattern as being El Nino-like, it's characterized by having a much more reduced zonal SST gradient between the east and west, and a much flatter zonal thermocline tilt. So because thermocline depth changes are one of the things that we're trying to reconstruct, I think I need to first explain how we do this using proxy data, because it's not very straightforward. As far as I'm aware, there's no direct measure to reconstruct thermocline depth changes. We have to use some sort of indirect metric. And in this case, we're using one of the more commonly used ones, which is the upper ocean vertical temperature gradient. So this is simply just the gradient between the sea surface and the subsurface. And we can do this because this is why we need core sites that have both sea surface and subsurface temperature data. So we can compute the temperature difference between these two levels to get this vertical delta T. And to illustrate how this works, we can look over here at this figure. So here on the y-axis, we see water depth, and on the x-axis, we have temperature. So what this is showing is two different types of water column profiles. So the blue one is showing a profile with a shallow thermocline, and the red one, we're looking at a profile with a deep thermocline. And, oh, sorry. What we can see is that when we have a shallow thermocline, the temperature difference between the surface and the subsurface is pretty large. But when we have a deeper thermocline, the temperature difference between the sea surface and the subsurface becomes more reduced. So we can use the change in this vertical delta T to infer changes in thermocline depth. So for example, going from a deeper thermocline to a shallower thermocline, you have an increase in the vertical delta T value. The thing is that while it seems to work quite well, there are at least two important caveats. One is that we have to assume that the forems are calcifying at the same water depth all the time. So during the LGM, during the Holocene, they're always calcifying at the same water depth, which is a big assumption, but if it's not made, then we have no idea what the delta T means. It's no longer telling us something about changes in the water column structure, but it's rather just reflecting the forem moving up and down the water column. Another thing that we have to keep in mind is that the vertical delta T shouldn't be interpreted alone. We also need to see how big the temperature changes were at the sea surface relative to the subsurface. Because if you have a scenario like this, while in this scenario, the vertical delta T is changing, it's dominated by large changes at the sea surface, which reflects a change in upper ocean stratification more so than a change in thermocline depth. So in this scenario, we propose that for the vertical delta T to really reflect a change in thermocline depth, you need to also have a larger temperature change at the subsurface relative to the sea surface. And before we move on to the LGM, we first tested whether these four metrics that we use to reconstruct large-scale changes in upper ocean patterns, whether they work. So we tried to do this using modern data. So we use Argo data, and we use Argo data from a strong La Nina year and a strong El Nino year to kind of function as two end-member tropical Pacific patterns, first to test whether these metrics are able to capture these large-scale changes in upper ocean patterns. And these are just the three study regions that we focus on: the Western Pacific Warm Pool, Eastern Pacific Warm Pool, and the Eastern Equatorial Cold Zone. So if we first look at sea surface and subsurface temperature changes between an El Nino and a La Nina phase, so the surface changes are shown in gray and the subsurface changes are shown in black. We can see that temperature changes are larger at the subsurface relative to the sea surface. And this is important for us to later interpret what the vertical delta T means. So in all three cases, because subsurface temperature changes dominate sea surface temperature changes, when we look at the vertical delta T, we know that it does indeed reflect a change in thermocline depth. And if we then look at the changes in the zonal gradients, so at the surface and at the subsurface, we see that during the El Nino phase, the zonal temperature gradient is reduced. And this is consistent with what we know about the El Nino configuration. The interesting to note is that we see a larger change in the gradient at the subsurface, a larger change at the subsurface than at the sea surface. And if we look explicitly at changes in thermocline depth, we can clearly see that during the El Nino phase, the thermocline is shallower in the Western Pacific Warm Pool, which is consistent with what we see in the profile. And it's deeper in both of the Eastern Tropical Pacific regions. And we can now assess whether these changes in vertical delta T are consistent with what we just saw in thermocline depth changes. Because when we later move on to the LGM, we won't have, for the proxy data, we won't have actual estimates of thermocline depth. We'll just have the vertical delta T. So we need to ensure that this works. So what we see is that the vertical delta T is larger during El Nino years when the thermocline depth is shallower, which is consistent with how the delta T works and what we see in the water column profiles. And in the Eastern Pacific sites, we see that the vertical delta T is smaller when the thermocline is deeper during El Nino phases, which is again consistent with how the vertical delta T works. So basically, to summarize, our tests of these metrics using modern data suggest that they are able to capture these large-scale changes in upper ocean patterns, so we can then recalculate them using our LGM proxy and model data to see what kinds of changes we see during the LGM. So we can first look at surface and subsurface cooling during the last glacial maximum. So on the left-hand side, we have our proxy results, and the right-hand side, we're looking at the results of our model ensemble. And what we can see from the proxy results is that you have pretty different west versus east, especially when you look at the Western Pacific warm pool and the Eastern Equatorial cold tongue. There are very different degrees of cooling during the LGM. You have stronger cooling in the west and not so much weaker cooling in the cold tongue. And what's also really clear is that you have this subsurface warming signal in the Eastern Equatorial cold tongue, which you don't see anywhere else. And if we look at the model results, it's quite different from the proxy results. For one thing, sea surface temperature changes are pretty homogeneous, both in the east and west. You don't really have a strong contrast in the degree of cooling. And you also don't have any subsurface warming in the Eastern Equatorial cold tongue. And this is true if we look at all the models individually. None of these models show any indication of subsurface warming in the cold tongue. So now if we look at how the zonal surface and subsurface gradients change during the LGM, we see that proxy data indicate that the zonal sea surface temperature gradient and the subsurface temperature gradient both became reduced during the last glacial maximum. And so a reduction in the sea surface temperature gradient is consistent with a shift to a more El Nino-like upper ocean configuration. And a reduced zonal subsurface gradient is consistent with a flattening of the thermocline, which is also consistent with a more El Nino-like configuration. But if we compare our proxy results to our model results, there's not so much change in the zonal SST gradient, which is not surprising because, again, there's really no large noticeable east-west difference in the degree of surface cooling during the LGM. For the subsurface, where you do have more east-west contrast in the degree of cooling, you do then have a reduction in the subsurface zonal temperature gradient during the LGM, which is consistent with, again, a more El Nino-like upper ocean configuration. If we look then explicitly at simulated thermocline depth changes, we see pretty minimal thermocline depth changes in both the Western Pacific warm pool and the Eastern Equatorial cold tongue. And these are occurring for kind of different reasons. So in the Western Pacific warm pool, you have pretty large intermodal differences in simulated thermocline depth changes between the LGM and Holocene. So I think in the end, the model ensemble, you have a small signal because these have canceled each other out. Whereas in the Eastern Equatorial cold tongue, simulated thermocline depth changes are pretty small in general, which is why in the ensemble mean, you also have really small thermocline depth changes. So if we look at the model vertical delta T changes, which are in theory, a metric for estimating changes in thermocline depth, we can compare how these compare to simulated thermocline depth changes. And what we see is that for our proxies, they all indicate a reduction in the upper ocean vertical delta T during the LGM, which in theory would suggest that in all three regions, the thermocline became deeper. But if we look more closely, so as I mentioned earlier, when you interpret this vertical delta T, it's also really important to know whether this change is dominated by temperature change at the sea surface or the subsurface. So we can see that in the Western Pacific warm pool and the Eastern Pacific warm pool, this change in the vertical delta T is very much dominated by glacial sea surface temperature cooling. So in this case, the change in the vertical delta T is not a great metric for thermocline changes. So we don't interpret these as an indication that thermocline deepened in these two regions. However, in the eastern equatorial cold tongue, where this decrease in the upper ocean temperature gradient is partially caused by, or largely caused by, a warming at the subsurface, this could actually be an indication that the thermocline did deepen in the eastern equatorial cold tongue, which is also consistent with a more El Nino-like configuration. But obviously, it's not consistent with the simulated thermocline depth changes in the model ensemble. So to then summarize and put our findings into kind of the context of what we know. So as I showed you earlier, for the historical period, observations indicate that the zonal sea surface temperature gradient became larger. And this is because more warming has occurred in the Western Pacific warm pool compared to the Eastern Tropical Pacific Ocean. And models show something else. They show stronger warming in the east, which has led to a reduction in the zonal SST gradient and indicate that the pattern became more El Nino-like. And in the future, the predicted pattern of warming, according to models, is that we'll have more warming in the Eastern Tropical Pacific Ocean, which will then result in a reduction in the zonal SST gradient and a more El Nino-like pattern. And our study, which is based on the LGM, which is a low greenhouse gas situation, our proxy results show that there was stronger cooling in the Western Pacific warm pool compared to the east. So you had a reduction in the zonal sea surface temperature gradient, which produced a more El Nino-like pattern, whereas the models showed pretty minimal changes, so pretty even cooling in both the east and west. So not a great change in the actual zonal gradient. And if we take a simplistic hypothesis from our study, we would say that an increase in greenhouse gas concentration leads to an increase in the zonal SST gradient and vice versa. But obviously, the difference between the last glacial maximum and present day is not just characterized by the change in greenhouse gas concentration alone. You have differences in ice sheets, vegetation, etc. So it's not exactly just the change in CO2 concentration that's driving the change in the zonal SST gradient. But obviously, this is something we could test, for example, using other paleoclimate periods, especially ones from past warm climates that are characterized by high CO2. The issue with this is, for example, for the mid-Pliocene warm period, we still don't have enough data to do this kind of regional comparison. So until we do, it's difficult to do this kind of regional comparison and compare with models. So thank you for listening. And this is the study that I just talked to you about. It's been recently published, and you can scan the QR code if you feel like reading the article. Thanks.
Thank you very much. That was great. And so if you can stop sharing your screen, and I'll try and get Vince to share his. And so we've got maybe 1 or 2 moments whilst that's happening for any particular questions. Otherwise, I'll get people, if they've got questions, I don't see any hands popping straight up, to add them in the chat. And then once Vince has done his talk, we'll try and have a discussion together with all the points. But yeah, so maybe I'll pass over to you now, Vince.
Great. All right. Thanks, Alicia. And thanks, Chris. Can you hear me okay? Perfect. All right. So I think this talk should build pretty nicely off of what Alicia just shared. For quick introduction, I'm a graduate student at the University of Washington, and most of my PhD work has focused on paleo pattern effects. Before I jump in, though, I just want to mention that this work I'll be sharing has been a big team effort. It's been fun to collaborate across different modeling centers. We've worked with a lot of data assimilation experts and paleoclimate scientists. So it's been a very collaborative, kind of fun project over the past couple of years. So as Chris was introducing at the beginning of the seminar, the goal here is to provide a paleo perspective on this CMIP7 science goal, which is understanding pattern effects. So kind of like Alicia, I'll build on what she started off with and give some background and motivation for why pattern effects matter for modern day ECS estimates. And I'll give another kind of explanation, I guess, of what the pattern effect really is and how it works. And then I'll talk about how the paleo pattern effects that we've looked at impact ECS constraints. So I'll share some recent work that's mostly focused on the LGM, but I'll sprinkle in a little bit of a Pliocene in prep work as well. So the key piece of background that's necessary, I think, for understanding pattern effects is this global energy balance model for ECS. And what we're looking at here, hopefully you can see my pointer okay, is that when you add a forcing to this system, you get a radiative response. And that radiative response is parameterized as lambda times the surface temperature change, delta T. So adding CO2 is the forcing, change in F, a change in surface temperature causes a response, and eventually the system will reach a new equilibrium. And once the TOA imbalance goes to zero, so N equals zero, the surface temperature change is just the forcing divided by the feedback. And that works in all cases in this simple model, at least. For ECS, we just call the temperature change the ECS when the forcing happens to be a CO2 doubling and the feedback is that which is associated with a CO2 doubling. And we have pretty good constraints on the forcing piece, but the thing that we're really uncertain about and trying to constrain is the denominator, and that's what is the feedback in response to a CO2 doubling. So since we don't know what that idealized feedback is, what has been done is we turn to other lines of evidence to estimate that lambda from a CO2 doubling. And one source of evidence that is kind of where the pattern effect thinking all got started is this historical record feedback. So we can kind of use the historical record feedback, so that's energy budget changes going back to the pre-industrial or so, to estimate the 2 times CO2 feedback. But we now know, as Chris was saying, over the past few years, there's been a consensus that that feedback is not constant in time. It can change with different background states. It can change with internal variability. And it can also depend on the forcing that is applied if it's not just a CO2 doubling. So the way that we account for that inconstancy of climate feedbacks is we include a delta lambda term that makes the historical record feedback more comparable to a CO2 doubling. And that delta lambda term is simply estimated as what we think the difference is between the 2 times CO2 feedback and the historical record. And that's become often referred to as the historical pattern effect. And the reason why we're calling it the historical pattern effect is because the difference in feedbacks ends up mostly being due to different sea surface temperature patterns. And I'll explain the physics a little bit behind that, like Alicia did in a few slides here. But before getting into the physical side, we can get everyone up to speed on the latest estimates of modern day climate sensitivity. So a couple of years ago, Sherwood-Webb et al. Led this community assessment that combined multiple lines of evidence for climate sensitivity, and that also informed what went into IPCC AR6. And one of those lines of evidence was the historical record, as I was just describing. And it is now known to be important to include in accounting for how the feedback over the historical record is not the same as the feedback from a 2 times CO2 doubling. And when you account for that delta lambda term, you get a very different estimate of ECS from the historical record. So if you ignore pattern effects, you get the gray line. If you include pattern effects, you get this orange dashed line. And what that means is pattern effects seem to make the historical record a very weak constraint on ECS. It doesn't really give much information at all about how high ECS could be. what Sherwood, oh, sorry, I should also say just quickly here, the reason for that is because the temperature patterns are so different over the historical record compared to the long-term response to CO2. So Alicia was previewing this as well. In the long-term response, we have amplified warming in the Southern Ocean and in the East Pacific. Over the historical record, we've had some cooling and certainly delayed warming, at least in those same regions. So as that temperature pattern evolves to go from the left to be more like the right, we should get a much more sensitive climate and a more positive feedback parameter. To bring in some constraints on ECS besides the historical record, what Sherwood-Webb et al. Did is they also looked at process understanding of how individual feedbacks in the system operate, and then they looked at the paleo record. So this is where my work is focused, is on the paleo constraints. One angle was the Pliocene, that's a past warm period. And then there was the last glacial maximum, which was a past cold period. And you can kind of see here, although it doesn't jump out too strongly, is that the LGM provided the most evidence that helped rule out some of the higher values of climate sensitivity. So when you combine all of these different lines of evidence in a Bayesian framework, you get a PDF on the lower right that synthesizes this evidence and says that the ECS is roughly 3.1 degrees. And Sherwood-Webb et al. Said that the paleo record was really what was providing the strongest constraint to rule out high values of climate sensitivity. But the thing that was missing from the paleo evidence is they didn't consider pattern effects in the paleo record at all. So what we are wondering is, if you look at pattern effects in the paleo record, could you potentially end up with something more like the historical record? We wanted to test whether there are pattern effects that were missing in the paleo evidence that was accounted for in Sherwood-Webb et al. Before the paleo evidence, or before I jump into that, my kind of quick physical summary of how the pattern effect works is, if you were to define it in one sentence, it's that the net feedback parameter depends on what the spatial pattern of SST anomalies is. And the net feedback is made up of various components. And the two that are most dependent on the SST patterns are the cloud feedback and the lapse rate feedback. The schematic here that we're now looking at shows the tropical circulation and the east-west Pacific gradient of sea surface temperatures. So this is very similar to what Alicia was showing. And just to walk through a quick example of how the pattern effect operates, if we first zoom in on the East Pacific, where there's a temperature inversion at the surface and you have a lot of low clouds, if you increase the SSTs a little bit in the East Pacific, you reduce the strength of the inversion, and that gets rid of some of the low clouds, which lets in even more sunlight and heats up the surface more. So that's a local positive feedback from warming, reducing cloud cover, and letting in more sunlight. On the other hand, if we look at the West Pacific, if we warm up a little bit localized in this region, that warming is quickly communicated to the upper atmosphere. This is a region of deep convection, which then warms the whole upper troposphere and actually strengthens the inversion in the East Pacific and increases your low cloud cover. That reflects more sunlight and offsets the warming. So if you warm in the West, you get a strong negative feedback. If you warm in the East, you get a strong positive feedback. So different areas of warming give you different changes in the global radiation budget. This figure is a way to quantify that across the entire globe. So you can see what they've done here is run a bunch of patch experiments in a climate model, and this is just showing one of them, although these results are mostly consistent with some subtle differences across different climate models. What it shows is if you warm in certain regions, whether you get a positive or a more negative feedback from those regions. So as Alicia was kind of showing, the tropical Pacific stands out as being particularly important. If you warm in the West versus warming in the East, you get very different feedbacks. But what I want to kind of emphasize is important to also think about for the paleo record is, if you warm more at higher latitudes, you tend to tilt the scales toward more positive feedbacks. The overall climate feedback always has to be negative. That's the only way to get a stable climate. But if you tilt the scales towards more positive feedbacks by warming in these regions where you're outside of the blue, you're outside of the tropics, you're going to get a more sensitive climate. So keep that in mind as we start to look at the paleo SST patterns. So the reason why pattern effects matter for the paleo record is because of how they affect ECS constraints. Or that's one reason at least why they might matter. And what I'm going to show now is whether there are paleo pattern effects that have not been accounted for and how they affect those ECS constraints. To summarize how we typically estimate ECS from the LGM is first they come up with a feedback that's representative of what happened at the LGM on its own. So this is from adding up all the different forcings that were acting during the LGM. And as a quick note, I just want to say that these forcings, there's still a lot of uncertainty in them. And that's one thing that the paleo, especially PMIP community, could really help us out with, is constraining those forcings. We divide by the temperature change during the LGM, and that gives us the LGM feedback. And then we use that to estimate modern day ECS, which is the forcing from a CO2 doubling divided by the feedback from 2 times CO2. We don't know that denominator, so we use the LGM feedback as an estimate. And what we're going to do now that wasn't done before is also include a delta lambda term for the LGM, which represents the pattern effect at the LGM climate. And we can do the same thing from the Pliocene, and I'll show a little bit of that for some preview results later. The reason why we're pretty sure there should be a pattern effect for the LGM is because the spatial pattern of forcing is so different in the LGM compared to the modern day response to CO2. So here what we're looking at is just the simple pattern of radiative forcing from a CO2 doubling, and you can see that that's relatively uniform from well-mixed greenhouse gases. When we look at the LGM, on the other hand, you get the background forcing from reduced greenhouse gas concentrations, which you can kind of see over the oceans. And there's also these extremely strong localized forcings from the ice sheet changes, and some kind of sea level coastline changes jump out as well. You can assume that maybe those different patterns of forcing are going to give you different patterns of the response in sea surface temperatures. And as a quick preview, in prep work, or I guess in revision now, for the Pliocene shows kind of a similar structure, but just in the opposite direction. So the Pliocene had much smaller ice sheets over Greenland and a much smaller West Antarctic ice sheet, and also vegetation changes over the northern high latitudes that could potentially affect the pattern of response as well. So those different forcings should give us different SST patterns. Similar to what Alicia was showing, we're looking at on the left, the multi-model mean response of long simulations that are near equilibrium of a CO2 doubling. And then in the middle now, I'm showing the average of 4 different data assimilation reconstructions of the last glacial maximum. And the thing that really jumps out when you average over these different efforts to reconstruct the LGM, you can see that there's this amplified strip of cooling in the North Pacific and the North Atlantic. And those are regions where we think we're going to get more positive feedbacks compared to what's seen in the 2 times CO2 response. For the Pliocene, these reconstructions, one of them is now published and one is in revision, show similar story, but just different regions where the North Atlantic and the Southern Ocean have extra amplified warming. And that's from those, or potentially from the non-CO2 boundary conditions that are changing during the Pliocene compared to in a pure response to CO2 doubling. Before we jump into quantifying the pattern effect, just one quick slide that I won't get into too many details over, but it's important to understand why we might trust these paleo SST patterns a little bit more than the response that's just from coupled models alone. So what has been done over the past few years through paleo data assimilation is they take a model prior, and this is from, say, the PMIP community or PLIOMIP, where a bunch of different modeling centers simulate the LGM or simulate the Pliocene, and that gives us a prior uncertainty on what we think that state looked like. And then the proxy data comes in from, say, ocean sediments, for example, and that proxy data is compared to an estimate of the data that comes from the model prior. And to the extent that the proxy data and the models are different from each other, we can spread that information across the entire state estimate using the spatial structure of covariance that's in the models, and we can update account for the uncertainty in the update using the uncertainty that's in the model prior and the uncertainty that's in the observations. So that's just a quick primer on data assimilation. The main point is that we end up with a posterior that takes the dynamics from models, but also the information from the proxy data to give us an estimate of the best mean state and the uncertainty in our state estimate of the LGM and the Pliocene. That's the good news. The bad news is that 4 different efforts to do this have actually led to somewhat different SST patterns. So here I'm showing these 4 different reconstructions. And what you can see is that in certain regions, they are more consistent. In other regions, they differ quite a bit. The one thing that is important for us is where they all agree is this relatively data-dense region, especially in the North Atlantic and the North Pacific, where we have a lot of proxy data, and we can see that they all show this strong amplified cooling in the North Pacific and the North Atlantic. So the one thing that's consistent as a very large signal is going to be important going forward. The other differences are also going to be important to account for because they add to our uncertainty. So now we have the SST patterns. The final thing we want to do is actually account for or estimate the feedbacks that are associated with those different SST patterns. So we take advantage of this simulation framework that's using AMIP type simulations, where you only change the lower boundary condition, the SSTs and the sea ice, and you keep the forcings the same. And this is the way that feedbacks are now being estimated over the historical record runs, and you can separately quantify forcings by keeping the SSTs fixed and only changing the forcing components that are, say, in the atmosphere or the LGM. And the way that this works is we use the same global energy budget equation that I was sharing at the beginning of the talk, but we keep the forcings constant so we can ignore the F term. And then when we change the lower boundary condition, that gives us a change in the surface temperature and a change in the TOA balance. And that's how we can calculate what the feedback is. This has been done plenty of times for the historical record, just not so much for the paleo periods. The way that we get to the pattern effects now is we run one set of simulations that's a baseline with the pre-industrial SSTs. And then we run a simulation that has the 2 times CO2 patterns, and that gives us the feedback in this framework for a CO2 doubling. And then we can run the same AGCM experiments using the LGM reconstructions. So we can sample from the different ensemble members from those reconstructions and use all 4 of them to get an estimate of the uncertainty. And we can do the same thing for the Pliocene. Now I'll show the results of those experiments. Before I show the paleo results, though, this is just a reminder of what happened when they did this for the historical record. So over the relatively recent past in 3 different models, and essentially all of them, the historical record feedback was more negative and stabilizing compared to the long-term response to CO2. But when we put in our paleo SST patterns, we get a more positive feedback for the LGM and the Pliocene, and that's true in all of these models, and also a couple that are not shown here from GFDL and the Hadley Center. So the historical record had a positive pattern effect measured by the difference between these 2 feedbacks. For the paleo record, we get the opposite sign, where the paleo feedbacks are more positive than the 2 times CO2 feedback, so that gives us negative numbers. This means that it's going to be the opposite sign of effect when we account for pattern effects in the paleo record compared to the historical record. So a negative pattern effect would actually mean stronger constraints on modern day ECS from those paleo periods, which at first was a little bit surprising to us. So we wanted to make sure we understood what the mechanism for that is before we actually started changing the ECS constraints. Now, the way that it works is we get positive cloud feedbacks that are coming from the regions that are strongly affected by the non-CO2 forcings. So first on the left, what I'm showing is a spatial plot of the cloud radiative effect, the way that that affects feedbacks. So it's the local radiation change from cloud radiative effects divided by the global mean temperature change. If you integrated this across the globe, you'd just get the global mean cloud feedback. When you compare the 2 times CO2 result to the LGM result, you can see that there's this region, again, in the North Pacific and the North Atlantic, where you get a much more positive cloud feedback in the LGM compared to in the response to 2 times CO2 doubling. And the reason for that, that SST pattern being associated with more positive cloud feedbacks, that SST pattern is caused by the ice sheet forcing. This is, again, where the models really help us out, because in the model world, you can just prescribe only the ice sheet forcing and no CO2 changes. And you can see that only the ice sheet forcing causes the SST response in those regions. So because of the model experiments, we can identify that region as being associated with ice sheet forcing, not CO2 forcing. And since what we're trying to do for the future is constrain the response in the modern climate to a CO2 doubling, we don't want the ice sheet forcing from the LGM to be affecting our feedback. And that's why we need to account for the difference in feedbacks between the LGM and the CO2 doubling. For the Pliocene, we have some early results that, again, are somewhat similar in spirit, where the regions that end up being strongly affected by vegetation forcing and smaller ice sheets are causing more positive cloud feedbacks in that period as well. And I'll share that work hopefully in the future sometime. So now we know that the LGM feedback is more positive than the modern day response to CO2 because of the way that ice sheets affect sea surface temperatures. What we'll do finally is just account for that difference in feedbacks, delta lambda, in our ECS constraints. So we start off with the same lambda from the LGM that was in the Sherwood-Webb et al. Paper, but we're now going to include this delta lambda term that's estimated from a bunch of different model experiments, or 5 different AGCMs, and also from sampling the uncertainty that's across those different LGM reconstructions. So that's why we have a pretty big uncertainty on this piece, is because those different SST patterns, they all have a similar sign because of the North Pacific and North Atlantic, but there's still a lot of spread in how big this effect could be because we don't have full confidence in, say, the Southern Ocean or the tropical changes during the LGM. We start off with the likelihood that was in the Sherwood-Webb et al. Paper, but we do increase the delta T from the LGM to be aligned with the IPCC estimates and the latest reconstructions. So that's a little bit, one slight change to make climate sensitivity higher compared to what was in Sherwood-Webb et al. And then we account for the pattern effect piece for the LGM. And you can see that this has a pretty large impact on what ECS would be inferred from the LGM alone, because it's telling us that the reason why climate sensitivity looks positive at first glance from the LGM is actually because of how ice sheet forcing is affecting the feedbacks that we infer. When we combine that with all of the other lines of evidence, as Sherwood-Webb et al. Did, just this one change gives us a much tighter constraint on ECS compared to what would be in Sherwood-Webb et al. Without any paleo pattern effects. So this bottom kind of blue box here is Sherwood-Webb et al.'s ECS constraint, but now including the LGM pattern effect. And you can see that it gives us a pretty big change, and especially what the upper bound is on climate sensitivity constraints. My one comment before I wrap up is just that there's still a lot of uncertainty here, which you can see both in the pattern effect estimate and also in the forcings that are informing that lambda from the LGM in Sherwood-Webb et al. So there's still a lot of work to be done, we think, here on getting better estimates of what the ice sheet forcing was, what the vegetation, dust forcings, et cetera, for the LGM. And hopefully we can get more people working on that in the future, myself included. So just to wrap up here, what we found is that the paleo pattern effects so far seem to be helping constrain ECS, but there are still a lot of opportunities for progress. Our results show that the feedback is more negative in the modern climate compared to in the response to LGM forcings. That difference in the feedbacks is caused by the SST response to ice sheets, and that gives us more positive cloud feedbacks in the North Atlantic and the North Pacific. When we account for this, we get stronger constraints on ECS, and our revised LGM constraint, it doesn't change compared to Sherwood-Webb et al. The median estimate by too much, but it gives us a much stronger constraint on the upper bound. We have a paper out earlier this year in Science Advances on the LGM, and one hopefully coming soon on the Pliocene. And with that, I'm happy to take any questions along with Alicia, and thanks a lot for listening.
Thank you very much for that. So I can see that there's been a couple of questions have been put in the chat for Alicia, so maybe we start with one of those. Julienne, did you want to mention your question out loud?
Sure, I can do that. Can you hear me all right?
Mm-hmm.
Yeah.
Although I was not the first one to ask a question, so I don't. Does Tübingen want to go first? Maybe not. Okay, I'll wait for them to get ready. My point was, the last time I looked at this, which was a few years back, one of the important aspects of understanding the radiative response of PMIP models to forcings was this shortwave SST feedback. And it's the balance of multiple processes. I'm not going to get into it, but there's a lot of work by James Lloyd and Bélanger was another grad student who worked on this in between 2009 and 2013. Sorry, the gardener is going crazy next door. And basically, you could divide a lot of the models into some that had a purely positive feedback, some that had a negative feedback, and some that basically had a mixed feedback where it changed from positive to negative with the sign of SST. And I'm wondering, if you separate the models in your ensemble according to this, do you see different patterns emerge for, the ones that have a more El Nino-like or La Nina-like response? Basically, the argument being that in the real world, there's good reason to think that the feedback is of a mixed type. And so if you only take the models that have this kind of mixed response, do you see something that's more consistent with the proxies? Does that make sense? Or is it I can follow up by email as well.
It makes sense, but I haven't looked. I did notice that there seems to be at least like two, maybe streams of models. But I didn't know the reason why. But maybe this is something I can look into to see if this is a criteria I can use to maybe try to group the different types of model responses.
Great. Yeah, I'd love to hear that.
Yeah, thank you for the suggestion.
Sure.
Thank you. And did Elisa want to say something about the question from Tübingen, which was, I can pull it up.
Yeah, thanks. Great help from you both. Yeah, actually, we were just wondering a little bit if, since you're looking only into mid-Holocene, if you've also looked into PI control or anything historical. And yeah, if the results are similar to mid-Holocene or
I didn't show it here, but in general, the PI results are very similar to the mid-Holocene, sometimes identical. But I chose to use a mid-Holocene instead of PI because for a lot of the proxy records, we don't have like the core tops or the upper part. So we don't have a lot of data from the late Holocene period. Whereas for the mid-Holocene period, we do have more proxy data. So this is why I chose that period to use for comparison instead of the late Holocene or PI.
Well, thanks.
I have a question for Alicia, if that's okay.
Go for it.
Yeah, this one's somewhat simple, maybe a little bit related to Julian's question. I noticed that in some of the figures, it looked like the model ensemble was very certain, like the error bars were really small on some of their West Pacific and East Pacific SST changes. I was just curious, I would have guessed with 7 models that there would be a little bit more spread in what they were showing in their tropical SST changes, because I think of that as being a region where probably the different models have relatively different responses. So just curious whether I am misreading that, or if the model ensemble, the 7 different models, kind of what really did all have such a similar change in those regions.
Good observation. I used like bootstrapping to kind of like basically resample every grid point to derive the ensemble mean. So it's kind of like I think because of all the averaging on the Monte Carlo simulations, I ended up with so many data points that the ensemble mean ended up having really small error bars.
Got it.
I think that's basically what happened.
Okay, that makes sense.
Yeah.
And I can see there's another question for you now, Vince, since you're talking, from Tim, asking about whether you've looked at Earth system sensitivity or how that might fit into your framework.
Yeah, it's a great question, Tim. The short answer, I guess, I haven't calculated what the ESS would be, but the implication here is that the ESS is still quite high. What this would mean is if you're looking at things, if you want to know how big the temperature changes are after the ice sheets have equilibrated and including, the indirect responses, I guess, to CO2, that would mean that ESS is quite high. I'm not sure whether it necessarily is how it compares to what our estimates already are, but kind of what my work teases out a little bit is the ECS from CO2 alone is lower, but the ESS could still be quite high is the, I think, simplest explanation.
Okay, cool. And then I can see there's a question from Julien asking again, Julien again, but asking a different question, thinking about how your work compares to emergent constraints that have been trying to constrain ECS.
It's a good question. So I've seen some of the recent emergent constraints papers, and it's been a little bit since I've read them, but my takeaway was that they were finding that, especially, I think they've used the tropical SST change from the LGM to try to constrain ECS, hoping that that region would be less affected by things like ice sheet changes. And I think that over the past decade or so, I think there's like a Hopcroft and Valdez paper, Martin Renault, I think, has a paper on this. It seems like there's been a bit of spread. My PhD advisor, actually, Kyle Armour, has a paper on emergent constraints over the historical record. I think the related answer might be that if the models kind of have a common bias, it's difficult to use the ECS constraints. So if they are kind of all not getting the right SST pattern, that would bias all of the models in a certain way. And what we're finding is that the data assimilation changes the SST pattern by making the North Pacific and the North Atlantic changes much bigger than what the models have on their own. So that region that becomes really important for the feedbacks when we do the data assimilation is kind of biased low, I guess. The SST changes are biased low across the PMIP unsubtle. So they're not sensitive enough in the North Pacific and North Atlantic to the ice sheet changes is what it looks like. So I think that that would affect the ECS constraints, but I'm not quite sure exactly what direction it would, how it would influence things. And I haven't looked at it myself, but yeah, it'd be an interesting angle to follow up on.
Thank you. I've been told that Tübingen has another question. Go on.
Hi there. Yeah, thanks. Different person here. So my question for Vince was, so is the data assimilation process actually needed? And like, do we actually need the SST pattern like on the entire, on the 2D map? And why not just computing that from the local records? Would that make sense? I mean, at the end, we do want to get to the GMST, and we need to apply sort of factors onto the local records. But that's also what the data assimilation does. Yeah, do you see what I mean?
Yeah, I think so. My first take is I think the data assimilation is important to have confidence in the global patterns, because in order to do the way that we quantified the pattern effect, you do need a globally complete map in order to prescribe that in the model. So you have to have something that's globally complete. There are probably ways that you could estimate gradients and things like that from the proxy records alone is one angle. And you can definitely do what we've done in models alone. So the Dvorak et al. Paper that I mentioned for the Pliocene, which is currently in revision, is using just models to estimate the pattern effects. So there are ways that you can kind of think about this with proxy records alone, and you can do the estimates with models alone. But because there are so many potential biases or intermodal spread in the patterns, I think it's important to bring in the data assimilation to try to get a little bit more confidence and understanding of the uncertainty in the constraints. So you can do these types of estimates without it, but I think it's a very, very useful tool for helping us get more confidence in the pattern effect.
Okay, thanks, Vince.
Thank you. I'm conscious that we've got to, well, what in Europe is certainly supper time for some people, but we've talked for an hour, and it's been absolutely wonderful listening to you both and your talks, and I think that's been really helpful, and especially sort of the call for action for what PMIP can possibly contribute by constraining forcings more. So I'd like to finish it there and finish by thanking both Alicia and Vince for really nice talks. Thank you very much.
Great, thank you.
Thank you.
Thanks, Alicia.
And
Thanks
I will
for
stop the
being
recording.
here.
That's all right. Thanks for coming along.